Okay, so I was asked this question by an IB student. To what extent does the axiomatic system in mathematics provide certainty in our understanding of the natural world? And that's a very deep and complex question, but let's try to analyze. So, an axiomatic system is something that helps our thinking. It helps us to systematize and make our thinking about very vast and infinite mathematical realms captured by a finite set of axioms, and it helps us to systematically think about realms which otherwise could be very vague and big and infinite and difficult to capture by human mind. So, for example, we have axioms in group theory, which is a mathematical term for symmetry, the study of symmetries. And in study of symmetries, we have a number, like small number, 3, 4 axioms, which describe what do we minimally require from some system which has symmetries. And once we have this small set of axioms, now it becomes kind of clear in our head what it means to talk about symmetries, because otherwise symmetry is a very vague notion. You ask an artist what is symmetry, and he can give you a lecture for a long time, and still he will give examples, and then you will be left with a feeling that if you had to say something about all symmetries, you wouldn't be able to do that. In mathematics, we describe symmetries with axioms, which means that on one hand we'll leave out probably a lot of things that an artist would still classify as symmetric. Mathematicians kind of make it rough, so we state like this is what we mean by symmetry. This is exactly this and nothing else. But what it enables us to do, enables us to prove things about all symmetric objects that are in this context symmetric, as well as understand what are the limits of our understanding. So if something cannot be proved from these axioms, then we know that statement is not something that we can consider to be a universal property of symmetric objects. The reason axioms became prominent also in foundational mathematical questions is famously, like the way we tell the story today, is because of the Russell's paradox. Now, the history of logic and set theory is complicated, but one way to describe what happened was that Bernard Russell, an English philosopher, came with the notion of the set of all sets, and the subset of that set, which consists of all sets which are not members of themselves. So as Russell envisioned, that entire mathematics could be described in terms of sets and membership relations between those sets. And the reason he wanted to do that was precisely because he wanted to kind of capture the entire mathematics somehow. And here we kind of come to this catch that mathematics kind of suffered for a long time, is that even though mathematics is supposed to be very precise, if we describe mathematical notions with English language or any other natural language, we can never be completely certain what are the underlying assumptions that are needed for these notions to kind of consistently exist. So when we say things like the set of all sets that do not contain themselves, we are not aware of what are the mathematical assumptions that are needed to even make a statement like that there exists such a set. Just to understand what I'm talking about, imagine instead of sets, imagine books, and a book can be a catalog, and it can be a list of other books. So imagine a library which has thousands of books, and then it has one book which lists all the books in that library. Now that book can have itself in that list, or it might not have itself in that list. So a book may list itself or not. And in the same way, a set can contain itself or not. So if we take the set of all sets which do not contain themselves, we end up with a paradox, because that set, if it contains itself, then it doesn't contain itself, right? Because if it contains itself, then it's such a set which does not satisfy the property of not containing itself. So, but that set was supposed to contain only those sets which do not contain themselves. So then it would not contain itself. But if it doesn't contain itself, then it's a set which doesn't contain itself. So it should contain itself. So we end up with this famous conclusion that that set contains itself if and only if it doesn't contain itself, which is a contradiction. And mathematicians got puzzled. Bernard Russell got puzzled, and the solution is to realize that this description, the set which doesn't contain, the set of all sets which do not contain themselves, is vague. It's not based on any formal system. It wasn't described within some axiomatic system. So when we start axiomatizing mathematics, we realize that we cannot even define such a set. It's impossible to talk about the set of all sets, or there is no way. It's like talking about something, something so transcendental, beyond any description. If you try to talk about the set of all sets, like talking about within mathematics, to talk about all of mathematics, it's impossible. That's the conclusion we have learned now after Russell. It was a long and very rocky road. In fact, if you're interested, I recommend reading a very cool book called Logicomics. It has been translated to many languages, so it's a fun comic book, which is it's about the history of logic, in fact, but it's surprisingly easy and fun to read, so I really recommend it. Given the topic, I mean, you wouldn't expect it to be so much fun. Another example of a axiomatic system is the axioms of Kolmogorov of probability theory. This is a very easy to understand example, so that's why I'm giving it here. It says that the probability of some event is between 0 and 1, so it's either, it must be at most 1, because if it's more than 1, then it doesn't make any sense. Probability of any event is at most 100%, and it's at least 0 because it cannot be negative. So, but I'm describing the intuition behind it, but this axiom is stated as a defining property of what probabilities should be in mathematics, right? Then the second axiom says that the probability of something happening is 1. And the third one says that the countable, and this is a bit more complicated maybe for you guys, but countable union of events which are disjoint. It doesn't say here that they're supposed to be disjoint, but if they're disjoint, then the probability of the combined event is the sum of their probability, individual probability. So these three axioms are intuitively true about probabilities, and Kolmogorov realized that if we state these three axioms, then we can derive, then it basically captures entirely the idea of probability theory. And once we have something like this really systematizes our thinking about probabilities, about probability theory, because then whatever we can derive from only these three axioms holds for all probability spaces on the one hand. On the other hand, if we want to check if something is a valid probability kind of space, then we need to only check these three axioms, and so on and so forth. So now we're kind of coming to the question, the original question, which does it give us certainty about the natural world? Well, yes, because it gives us certainty about our own thinking about the mathematical descriptions of the natural world. So we know that probabilities are used to describe natural world, and if we have a systematic formalization, like an axiomatic approach to probabilities, then it definitely gives us certainty about what we're saying about natural world when we talk about probabilities. The axiomatization of mathematics, the set theoretic axioms of ZFC, You should Google that if you're interested. ZFC is what we consider today the most accepted axiom system that captures most of mathematics. It cannot capture all of mathematics because of the Russell paradox, basically, but it captures most of it. Also, there is Gödel's incompleteness theorem, but we set that aside for this video. But the ZFC axioms gives us certainty about how to, what are the things that we can prove rigorously, and what are the things that are kind of left beyond our basic intuition, beyond our basic understanding. Examples include the continuum hypothesis, which cannot be proved from these ZFC axioms, but this is very abstract, so I wouldn't call that really natural world, unless you consider the realm of abstract mathematics as part of natural world. Why not? But if we're talking about physics or other phenomena outside of mathematics, then what this gives us is foundation for mathematical thinking, which then kind of helps us to be certain about the way we apply mathematics to other fields. On the flip side, we have to be careful when applying axiomatic approach to natural world, because very often as mathematicians we may assume some axioms which do not actually hold in the world out there. I give you a very funny example. In mathematics, we often assume that the distance from A to B is the same as the distance from B to A. And you might imagine that that is a good axiom, the good assumption. It's actually an axiom in metric topology. So one of the axioms of what is it to be a metric is that the distance from A to B is the same as the distance from B to A. But imagine that I'm driving a car and I'm measuring how much petrol it takes me to go from A to B. And it could very well be that there is a long uphill road from A to B, in which case there's much more petrol and even time goes into traveling from A to B than it takes to travel from B to A. Or imagine there is a bus route which is circular. I mean, there are many examples of this. Even in Helsinki, where I live, there are bus routes which go in circle. So if I want to use this bus to go from here to here, then it's a short bus ride. But if I want to go from here to here, I have to go all around like this, because there is no bus which goes back the exact same way backwards. And sometimes, even if there is, there could be a rush hour. It can be, so basically you understand what I'm talking about. So the distance for any natural, the question is about natural world. Now, for any natural situation, it's not true that the distance from A to B is the same as from B to A. And mathematicians often forget that. So that kind of stuff, right? So there is a danger in applying axioms in natural world, but if we are careful, then everything should work out.